In this Capstone project, we're going to talk about the design and development of a photovoltaic inverter for the Internet of Things residential application. The team members are Mark Redcliffe, Arslan Kwam, Adefumlola Okunawa, King David Ekenkwe, with our contact information listed below.
The problem we are trying to solve in this Capstone project is the issue of inverters with low efficiency. As the world moves towards a greener future, the need for clean, efficient power becomes much greater. A typical inverter used for photovoltaic applications runs at approximately 70% efficiency. Some of the challenges that are causing the inverter efficiency to remain low are the quality of the electronic components that are used, the control methodology of the system, the number and size of the components. Also, there are environmental factors, such as operating temperature and water, that affect this. Another factor that affects the efficiency is the cost. As the quality of the components and the quality of the manufacturing increases, so does the cost. These systems can also lack portability and therefore are unusable in remote locations. There are many existing solutions for an inverter for photovoltaic applications, including a DC to DC boost converter using proportional integral controller, a DC to AC inverter using a MOSFET transistor, a DC to DC converter using a pulse width modulation controller with a maximum duty cycle of 90%, and a DC to AC inverter charging and discharging from a battery. Our proposed solution is to use an integrated boost half-bridge DC to DC converter that feeds into a DC to AC inverter with a full bridge configuration with 4 switches and 2 inductors. This design gives little leakage current and a smooth AC output voltage. The control for this design is the Arduino Nano 2040 RP Connect. Here's our complete system, with the solar panel that feeds into the inverter that's housed in a 3D printed case that then feeds the security camera. We tested our design in the lab with a DC power supply set to 6 volts, and the system output showed 50 volts peak to peak with a 25 volt maximum output on the oscilloscope. In order to verify that our system was working, we took the solar panel and their circuit outside and connected everything. We then used a multimeter to test the output voltage, and it came out to be approximately 19 volts AC RMS. Part of the IoT portion of this project includes the built-in functionality of our security camera. This camera connects through Wi-Fi to an app that controls it. Through this app, the user can move the camera, record and download the videos, turn on lights and sirens, as well as use an intercom feature to talk to someone wherever the camera is located.